Alright, in this section we have a couple theorems to look at. The first one is called Rolle's theorem. So copy this definition down. So we're talking about a function that is continuous over the interval from a to b, including the endpoints, and differentiable, but this time not including the endpoints. Okay, so the derivative doesn't have to exist at the endpoints. And if we have this third condition where f of a equals f of b, all right, now that's referring to the y values being the same height. Then, if those three conditions are met, there is going to be at least one point somewhere in between our interval where the derivative is equal to 0. Now, if the derivative is equal to 0, that means we have a horizontal tangent line. So what might this look like? Well, draw a function where we start with endpoints, which we're going to call a comma f of a and b comma f of b. Notice how these endpoints have the same height. And then we can draw a function that is continuous and differentiable everywhere in between. Well, it's guaranteeing that somewhere on the inside we're going to have this point which we're calling c, and its y value would be f of c. So all of this is referring to a function f. So this theorem is guaranteeing that at this point f prime of c, the derivative, is equal to 0. So in other words, you are guaranteed to have a horizontal tangent line. But again, don't forget about the condition where the y values have to be the same. If you have a function where the y values are not the same, then it's not going to apply. So I'm talking about something like this. Okay, those y values are not the same. So here, Rolle's theorem doesn't apply. All right, because f of a is not equal to f of b. So there's no guarantee that a derivative would equal 0 in between. As you can see here, that's a positive slope everywhere. There's never going to be a horizontal tangent line. Okay, so here's an example of Rolle's theorem in action. Suppose you have this function f of x equals blah 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 over the interval from 1 to 7. We want to show that Rolle's theorem applies, and then we want to find the x value guaranteed by it. Well, to show that it applies, first of all, we know that f of x is continuous because x squared minus 8x plus 12, that's a nice parabola. We know that f is continuous, and we also know that this function is differentiable everywhere in between, right? Parabola, quadratic, whatever you want to call it. There's no sharp turns at all, okay? So it's going to be continuous and differentiable. And the third condition, recall, is that we have to make sure that these endpoints have the same y value. So if you were to drop 1 into this function, you're going to get 5. If we drop 7 into this function, you're also going to get 5. So that confirms that f of a equals f of b. So we know that the three conditions have been met. Now, to find the x value guaranteed by it, we need to simply find our derivative, and then we're going to set it equal to 0 and solve. So our derivative, this is pretty easy to find, 2x minus 8. We're then going to set it equal to 0 to find where we have that horizontal tangent line. Well, that's going to give us x equals 4. And let's just support this graphically. If you were to sketch a quick picture of this function, the y-intercept is 12. It would drop down like this, open upward. Okay. Now, we know it's going to pass through the point 1, 5, and 75. Okay, so it guarantees that we're going to have a point where the slope is equal to 0. Well, that happens when x is 4. Okay? All right, now we're going to look at what's called the mean value theorem. And here we're dealing with only two conditions. And these two conditions here are the same conditions that Rolle's theorem had. All right, it still has to be continuous, it still has to be differentiable. Okay? But the third condition of Rolle's theorem, where the y values had to be the same, that's not applicable here. So this guarantees that there's going to be at least one point, which we're calling C, somewhere between A and B, not including A and B, okay, where f prime of C equals f of B minus f of A all over B minus A. Well, there's a few different ways of interpreting this. This f prime of C, since it's a derivative, we are referring to an instantaneous rate of change. And over on the other side here, f of B minus f of A all over B minus A, that is an average rate of change, which we saw earlier in a previous video. Okay, so in other words, this is the slope of the tangent line, right? That's what a derivative is. And this is really the slope of a secant line. Okay, this is your traditional change in y over change in x, right? This is your rise over your run. Okay, so we're looking at the slope between 2 points, and then over here we're looking at the derivative. So we're talking about a situation where maybe you have an endpoint there, you have a function that maybe looks like that. Notice it's continuous and it's differentiable everywhere in between. So this point, let's refer to as A comma f of A, and this point up here, B comma f of B. Okay? So if we were to look at the slope between those 2 points, okay, that's called a secant line, all right? So that's our secant line. If we were to look at the slope between those 2 points, the slope of that secant line, also known as the average rate of change on this function between those 2 points, this theorem guarantees that there's going to be another point somewhere where the slope of its tangent line is going to be the same. So here's my tangent line. The slope there is going to be the same as the slope of the secant line. So we know that if two slopes are the same, the lines are parallel. So you can see in our diagram here, these lines are parallel. Okay? So let's look at an example where we see this in action. Alright, so in this example we have x cubed as our function. Our interval of interest is from 0 to 2. Again, those are referring to x values. We want to show that the mean value theorem applies here, and then we want to find the x value or values guaranteed by it. Well, y equals x cubed. This is continuous and differentiable everywhere. All right, everywhere in its domain. So it's certainly going to be continuous and differentiable from 0 to 2. Okay, so you should know what this function looks like. All right, we're looking at something like this. Okay, now our points of interest are right here at 0, and let's say up here at 2. Okay, so at 0, we know that the y value is going to be 0, and at 2, we know that the y value is going to be 8, right? 2 cubed. So we know that f of 0 is 0 and f of 2 is 8. Well, let's first find the slope of the secant line. Okay, the secant line again is that line connecting these 2 points. So let's find the slope between those 2 points. Well, it's simply the change in y over the change in x. So the y values, we have 8 minus 0. The x values, we have 2 minus 0. So that's going to give us 4. Okay? So that's our slope of our secant line. Now, this theorem guarantees that there's going to be a point somewhere on this curve where the tangent line has the same slope as the secant line. So that slope of 4 needs to show up somewhere. So to find it, we need to find our derivative. So that, of course, is 3x squared. So what we're going to do is, because this, and again, this represents the slope of the tangent, this theorem guarantees that this tangent line and this secant line slope are guaranteed to equal one another. So to find where that happens, we simply set them equal to one another. So if we solve this, divide our 3 over, we have 4 over 3. X would then be plus or minus the square root of 4 over 3. Now, because our interval is from 0 to 2, we are going to reject this negative because that is not within our interval of 0 to 2. So, x equals the square root of 4 over 3 is going to be our only applicable answer. All right, and if you were to punch that into the calculator, you would see that that is approximately 1.15, which of course is somewhere within our interval. Okay, so this would be the value guaranteed by the mean value theorem. Okay, if it's multiple choice, that's what you're going to see as your answer. Although you could possibly see them rationalize this or simplify it. This would be the same as 2 over the square root of 3, which would be the same as 2 radical 3 all over 3. Again, if it's multiple choice, you could see any of those possibilities.